Let's take your attendance first. Okay, boss. Okay, so after a long holiday, 1 week, so now you have to be like another 6 weeks to go, right, for your trial. So planning is be finishing like 5 weeks. 5 weeks to finish the syllabus, just 1 week for your revision. Okay. We'll be having extra class. I plan to give it on Saturdays. Okay. If any concern, you can WhatsApp me. Saturdays most probably like 2 o'clock. Okay. On and off. Not every week. So I just monitor. I try to finish it in 5 weeks. Okay. So today we halfway of discussing your 10th topic, right? Induction. Okay, we go back. Let me shut down the light. Switch, shut down the other half of the light. Is it okay? You want me to on the light? Is it fine? Yeah. Okay, so this is the one a tricky one, very short topic, but tricky because of the idea. So recall back what we learned. We just spent one class that day discussing this topic, right? Okay, so electromagnetic induction is about what? It's about your generator, generate electricity. Okay, so you supply what to the generator? I told you there is already magnetic field inside the generator at the side, and we supply force. We apply force many ways. Hydroelectric dam, the water pushes the turbine. Nuclear reactor, the steam pushes the turbine. So we apply force until you get EMF. We got electromotive force, which end up closed circuits, end up producing current. Okay, so generator works based on 2 laws, and 2 scientists discovered, give some ideas about how to make a strong generator. But first thing, the unit introduced for you is about magnetic flux, right? So you have to know what is meant by magnetic flux. An important quantity linked to generator. Okay, so yeah, so what is magnetic flux? It's a product of magnetic field strength and the area which perpendicular to the magnetic field strength. Okay, So how do you rise the flux? How you can increase the flux? Either make it the magnetic field stronger, okay, the field line is quite close, or you make the greater area. Okay, there are two ways. And make sure the area and the magnetic field is like perpendicular to each other. Yeah. So the unit is first time you come across with the unit. What is the unit? It's a Weber, right? Introduced to you Weber. Then we talk about something called magnetic flux linkage. Magnetic flux linkage just multiply with the N. NBA cos theta is it's called magnetic flux linkage. You have one wire, one round. The flux is very little, but you have 10 turns of wires. Magnetic flux linkage, the total flux become 10 times. Okay. Okay, so the day we did what is the flux of this window, right? B dot A, magnetic field strength times the cross sectional area. Okay. The B was 90 degrees. We done this, right? We done this. Do we? Okay. Okay. Then we talk about Faraday's law. So we talk about Faraday's law. Okay, what Faraday's law says? How do you get great EMF? The EMF induced is directly proportional to what? Rate of changes of magnetic flux linkage. So rate of changes of magnetic flux linkage. Okay. Yeah. So rate of changes of magnetic flux linkage. Okay. So in formula, what is the formula? The EMF is negative d psi over dt. In terms of differentiation formula. Okay. You can say changes in magnetic flux over the magnetic flux linkage over the time. So it's like BAN over the time, the EMF. Okay. So you want to get great EMF, make sure your magnetic field is the strongest as possible. Try to have a big area as possible for the coil. Get more number of turns and do that in a short period of time. Okay. Change the flux as fast as possible, rate of changes of flux. Okay, so we discussed this the day, right? And we are stopped at Lenz's law. Okay, just halfway of discussing Lenz's law. Okay, Lenz's law just did a little addition. What is the addition he did? He just described, okay, when you change the flux, EMF will be induced in the coil, in the conductor. Okay, let's say you have a magnet, you have a coil. Okay, you take the coil, cuts the magnetic field line. Okay, so who will experience the EMF? The conductor will experience EMF. Okay, actually the magnet also will experience EMF, but our focus is to the EMF induced in the conductor. Okay, so what Lenz said, okay, you have EMF. Okay, let's say the conductor used is a coil. Let's say it's a coil, it's a loop. Okay, so because of closed circuit and it has a EMF, so you're going to generate current. Current will be initiated. The current flow is which direction? Is it clockwise or anti-clockwise? So the direction was explained by Lenz's law. Which direction the EMF will be induced? Okay. So what Lenz's law said states that the direction of the induced electromotive force is always such that to oppose the change producing it. Okay. Actually the EMF, the current flowing inside the circuit because of this magnetic effect, actually the electron don't want to flow. The electron is flowing. What is the mission for the electron? Just to oppose the change. You don't want to be created. Okay. So you oppose the change. Okay. What type of change happens? Either flux could be rising or decreasing. You want to oppose the change. When the flux is rising, the current will try to decrease the flux. How we can decrease the flux? By creating a secondary magnetic field opposing or enhancing the original magnetic field. Okay. So this is towards the end of lesson, right? We did. Okay, for this, we continue from here. So we go to the slide. Yeah, okay. So that day we discussed this, right? Okay, look at the third diagram. Focus to the third diagram. Okay, so the magnet is going into the page, right? The magnet is going into the page. Can you understand why the current flows here is a clockwise direction? How Lenz can explain this? When the south is get into the coil, what happened to the flux? Flux is rising or decreasing? Flux is increases, right? Flux is increases. So flux increases. Flux is what I've shown, B dot A. So flux is increases. So what the EMF will be induced in this coil? So the EMF must oppose the change. What change happening? Flux is increasing. So what the current should do? Increase the flux or decrease the flux? What the current should do? Must increase the flux further or must decrease the flux? Must decrease the flux. Must decrease because it opposes the change. What change happening here? Flux is rising. Okay, so you must decrease the flux. How you can decrease the flux? Producing a magnetic field same as the original magnetic field, oppose the original magnetic field. You want to decrease the flux. Okay, flux is rising originally. The current want to decrease the flux. Okay, because it opposes the change. So how you can decrease the flux? Creating a magnetic field same direction as the original magnetic field, oppose the original magnetic field. Opposes the original magnetic field, right? Okay. Where's the original magnetic field? Which direction? Downwards, right? The B. Okay. So the current must produces a flux is rising, right? Sorry, flux is rising. Not Evo. Flux is rising. Yeah, flux is rising. Yeah, flux is rising. The magnetic field is which direction? The magnetic field is not downwards, right? The magnetic field is upwards, right? The B is upwards because it's a south pole magnetic field upwards. So the current should produce magnetic field which direction? Downwards or upwards? Should be downwards. The current should produce a magnetic field downwards. Okay. So by using one rule, right hand grip rule. Okay, use your right hand grip rule. So your thumb point downwards. So your finger follows clockwise direction. So current should flow clockwise direction. Okay. So the direction of current is obtained by using Lenz's law. Okay. So if they ask you to explain in an exam why it is in clockwise direction, the first point you must tell is what happened to the flux. Okay. Flux is rises. The magnet get into the coil, flux rises. Okay. Then second, before you tell the direction of the current, you introduce the Lenz's law. You see, the direction of the induced current or induced EMF is such as to oppose the change which produces it. Okay. So therefore, by using a right-hand grip rule, the current should flow clockwise direction. Okay. Any questions so far? I know, new idea. We will do more questions to strengthen the idea. Okay. Actually, Lenz's law is based on conservation of energy. Okay, it's based on conservation of energy. Okay, Lenz's law is statement of the law of conservation of energy. The induced current sets up a force on the magnet, which the mover of the magnet must overcome. Okay, like you push the magnet downwards, the coil is going to create a magnetic field upwards. So you have an opposing force. Okay. So you have to overcome that opposing force, okay? So, but you're still moving downwards. That means what happened? You're doing work, okay? Right? There is opposing force by the current, okay, when you move downwards. So you have to do work, okay? The work done by you is converted to electrical energy, okay? The work done in overcoming this force provides the electrical energy of the current. Okay, you got the current. It's actually based on, it's actually conservation of energy. Okay. So in exam, they'll ask you to find out which direction is the current is flowing. Okay. So oppose the change. Okay. So one example. Okay. Look at the question and the solution. So flux density between the poles of magnet is 0.08 Tesla. A small coil of area of 6.5 centimeters squared. It has a 250 turns. It splits with its plane normal to the magnetic field. So the trigo is 1, the value. The coil is withdrawn from the field in a time of 0.26 seconds. Withdrawn from the coil. That means you have the coil first. Okay, you have the coil. There is a magnetic field. Okay, then what happened? The coil is totally removed from the magnetic field region. So the magnetic field is just here. The coil is totally removed from the magnetic field. That means what happened to the final flux? Final flux become 0, right? Because not overlapping with the magnetic field. So what happened to the coil? The coil experienced changes in magnetic flux. Okay, so what happened to the coil then? Induced EMF, current should flow in the coil. So first question, what is the magnetic flux through the coil when it's between the poles of the magnet? So the original magnetic flux is BA cos theta, of course cos theta because it's normal, so 0 degrees, so it's 5.2 times 10 power negative 5 Weber. This is the initial flux. B dot A, the magnetic field times the entire area, B dot A. Then what is the change in second? What is the change in flux experienced by the coil? Change in flux is the final flux minus the initial flux, right? Which flux becomes 0? The final flux is become 0, right? Because the entire area not overlapping with the magnetic field anymore. Totally removed from the magnetic field, so flux becomes 0. So change in flux 0 minus this, you get negative 1.3 times 10 to the power negative 5 Weber. So this is a change in flux. Negative sign indicates that the flux is decreasing. Okay. Cambridge mark scheme, change in flux, they always go for positive. Okay. They like modulus change in flux. Okay. You put negative also doesn't matter. Okay. Final minus initial. Okay. So then finally, what is the average EMF? Just change in flux over time. Change in flux, we take it as just the magnitude. Okay. Over time, so again 0.05 volt should be generated in that coil. Okay. So yeah, so flux P dot A, you've got n turns, let's say 50 turns, then you must go for magnetic flux linkage, multiply by n. Okay. This is only one coil just P dot A. Okay. Okay, this not involve Lenz's law, just Faraday's law calculating. Okay, so let's move on. Okay, so this is the little challenging. Okay, so 2 minutes for you. Look at question A, just part A. Okay, lots of wording. There is a rectangular coil placed in a magnetic field. Cross means the magnetic field is into the page. And the dimension was given 10 centimeter, 12 centimeter. Okay. And this coil has 30 turns. It has 30 turns. 30 turns. Okay. And the magnetic field, original magnetic field is 2.5 Tesla. Okay. So when the coil is jerked to the left, cutting the magnetic field lines perpendicularly, calculate the average induced EMF in the rectangular coil if it is moved out of the magnetic field in 0.5 seconds. Okay, come on, 1 minute. Next slide, of course, the answer. Try to figure out how the working should be. How much do you think? The entire rectangular has been moved away from the magnetic field entirely. How much is the EMF to be induced in this rectangular coil? So EMF is what? Rate of changes of magnetic flux linkage. Okay, rate of changes of magnetic flux linkage. Okay, so EMF sometimes so final flux 0 or initial flux 0? Total final flux 0, right? Final flux 0. Initial flux, how do you calculate? Initial flux NBA, right? N number of turns, P the magnetic field strength, A is the cross-sectional area, NBA. So 0 minus NBA over the time taken for this change to happen, 0.5 seconds. Okay. So what's the EMF you got? How many volt? So 0 minus NBA over the time, right? Okay. So yeah, you get 1.8. So 0 NBA, 0 minus NBA over the time. So it should be 1.8 volts should be generated in the coil. Okay. 1.8. Final flux minus initial flux over time. Okay. NBA. Okay, now extra question. So 1.8 volt was generated. So 1.8 volt was generated in this coil. Okay, now because it's a closed circuit, current should flow. Okay, tell me which direction current should flow? Clockwise direction or anti-clockwise direction? Use Lenz's law. Identify. The current EMF generated is 1.8 volt. Okay, closed circuit current should flow. Next time also they ask, okay, EMF is generated, why there is current flowing? The reason is what? It's a closed circuit. Okay, unsafe closed circuit. Closed circuit, current flows. Clockwise and anti-clockwise. Just 1 minute for you to think. Lenz's law state what? It opposes the change. The current flow in such a way that it opposes the change. What changes happens here? Flux rising or decreasing? And move away from the magnetic. Flux is decreasing, right? Flux is decreasing. Current should do what? To oppose the change. Okay, so current, because flux is decreasing, current should rise the flux or decrease the flux. Current should rise the flux one. Okay, because decreasing one, flux decreasing, you want to oppose the change. So you increase the flux one. How the current can increase the flux? Producing a magnetic field, same direction as the original magnetic field, oppose the original magnetic field. You want to increase the flux. How do you can increase the flux? Strengthening the magnetic field or weakening the magnetic field? Weaken the magnetic field. To strengthen the magnetic field, right? To rise the flux back. So, right-hand grip rule. So, your magnetic field generated by the current should be into the page or out of the page. The original magnetic field is where? Into the page. So, the current should strengthen the magnetic field, right? Because you want to rise the flux. Flux is dropping, you want to rise the flux. So, the magnetic field produced by the current should be into the page. Okay, should be into the page. So current should flow which direction? Should flow clockwise direction. Current should flow clockwise direction. Those thought it should be clockwise, good. Okay. Based on Lenz's law, you must identify the direction of the current. Okay. What Lenz's law stated, the induced current, the direction of the induced current or the direction of the induced EMF is such as to oppose the change which produces it. The change check, is it flux rising or flux decreasing? Okay. So this case, extra question A, the direction of current should be clockwise direction based on Lenz's law. Okay, so settle with A, hope you got the idea. Now look at B. B, go to the point. B, the rectangular coil is moved back into the original position. Okay, the field is 2.5 Tesla. Okay. Now, what they did, if the magnetic field density decreased from 0.5 to 0, this is what they did. The coil is now inside the magnetic field. They never moved the coil anywhere. The coil is in the magnetic field, but now the magnetic field strength is reduced. The field strength is reduced without moving the coil. Okay. Is it any flux change going to happen to the coil? Can happen, right? Either you change the area, move the coil, or don't move the coil, change the strength. Change the strength, also flux will change. Okay. P dot A. B change, flux change. A change, flux change. So it was magnetic field strength was changed 2.5 to 0 in 0.8 seconds. So what is the complete average in this EMF in this coil now? So again, final flux linkage minus initial flux linkage. Which flux linkage is 0? Final should be 0, right? B final is 0. So again, 0 minus NBA over the time now 0.8 seconds. Give you the EMF. Same idea. Changes in flux over time is your EMF. Okay? Final flux minus initial flux. Right? So P1, we don't want to waste time. We straight go to the solution. I hope this idea should be in your mind, right? B1. This is B1, right? So negative changes in flux. So final flux minus initial flux. Okay, over 0. We put the negative. Okay. Okay. As I said, if you go to the mark scheme of the Cambridge, the EMF they induce, they never put negative, just change of flux over time. The flux change, right? Of course, final minus initial sometimes give you negative answer, right? They make it as positive, like the changes always positive. Okay. So your final answer always become like a positive answer. Okay. No need to include negative. Okay, no need to include negative. Change of flux make it positive. That means big minus 4. Okay. The working given by Cambridge. The working here, this is the actual original working one. If you go to university level, let's say doing induction, this is how you should do. Okay. Okay. Final answer you give like this also is fine, no problem. Okay. So negative final flux minus 0 initial flux value, so over time you got 1.1 volt. Okay. Again, that's the big one. How's B2? Indicate and explain the direction of induced current in the coil. Okay, 1 minute for you. Let me check how many of you can get the answer. Tell me for B2. The current flow clockwise or anti-clockwise? Use Lenz's law. See how many of you got clockwise and how many anti-clockwise. 2.5 Tesla becomes 0. Coil experience flux change. So according to Faraday's law, EMF is induced. So current initiated. The current is which direction? Clockwise, anti-clockwise. Use Lenz's law. What's Lenz's law stated? The direction of the induced current is always opposed to the change which produces. What type of change happens? Flux rising or flux decreasing? Flux decreasing, right? Going down. So what the current should do? Rise the flux or decrease the flux? Current should rise the flux. We oppose the change. Right? So how we can rise the flux? Create a magnetic field, same direction as the original magnetic field, oppose the original magnetic field. You want to rise the flux. Current want to rise the flux. So must be same direction as the original magnetic field, right? So right hand green rule going in. So should be again clockwise, right? Should be clockwise. So the external magnetic flux is directed into the plane of the coil by Lenz's law. The induced current must flow in a clockwise direction, producing a magnetic flux directed into the plane. The coil restoring the decreasing magnetic field. Restore back the original flux. To oppose the change. So whenever they are asking for direction of the current, first thing you check, is it flux rising or decreasing? If flux is decreasing, current create a magnetic field, same direction as the original magnetic field, to rise back the flux. Okay, to oppose the change. Okay. But we as a human, we benefited from this act. We retrieve the current to light up your light bulb, to electricity is generated. Okay. Okay, yeah, so that's your part B. Part A, area change, move coil, you got EMF. Part B, magnetic field strength change, you got EMF. Okay, now part C. Another way of getting EMF. Part C is what? Magnetic flux density in B is increased to 4.5. Okay, it rise to 4.5 field. Find the induced EMF. If the coil is rotated through 90 degrees. Coil has been rotated through 90 degrees. Okay. Center axis. Center. Okay, let's say this is the axis of rotation. So it was rotated through 90 degrees. Okay, for 90 degrees. So this direction. So we are moving towards the generator now, right? Generator rotating the coil, right? I think A, B, C happens in your generator, right? We are turning the coil. Okay. We can't afford to do A. Where we going to displace the coil? We need a small space. We just rotate it. We can't do the B. It can be done. B be done in transformer. I told you. Transformer generate secondary EMF by changing the magnetic field strength. C happens in the generator. So what is the EMF again? Final flux minus initial flux over the time. Okay, changes in flux, magnetic flux linkage over the time. So which flux is zero? Initial zero or final zero? Turning 90 degrees. Turning 90 degrees, the area becomes zero, right? Okay, so magnetic field like this. Okay, turn like this, the area is zero. Zero area. Okay, only the side exposed, right? So final flux is zero. Initial flux NBA, right? N times E times the A. B is 4.5. A is the same A. 10 times 12. The cross-sectional area. N is 30. Over the time, 0.3 seconds. Yeah, so you should get this right. 5.4. Final flux should be zero, right? 90 degrees turn, no area. Initial flux NBA only 1.62, 0 minus 1.62, 0.2. Okay. In Cambridge mark scheme, what they're going to write here, they just put EMF, they're going to write changes of flux over changes of time. So flux, they just put 1.62 over the 0.3. Okay, so they give 5.4. Okay, this the working will be given in the mark scheme. Okay. As I said, they simplify. They always take changes of flux as follows. Okay. The original one, of course, negative must be there because of Lenz's law. Always final minus initial. So final minus initial here become negative becomes plus 1. Right? So choice is yours. You can go to this also if you want. Okay. Any questions so far? Here's the core idea. Okay. So we strengthen the idea further. Okay. Okay, another question. Here's the point. A solenoid. Is a solenoid. Has 600 turns. Radius is 5 centimeter. Uniform magnetic field at an angle of 30 degrees. Okay. Magnetic field is 30 degrees to the surface area. With the axis of solenoid, the field decreases. So now, they never rotate the coil. The flux is changed by changing the B. The field decreases at a rate of 0.4 Tesla per second. The field strength has been changed. The coil is permanent. Field strength change. Flux changing. Flux changing. So what is the magnitude of the resulting induced EMF? Okay. How much EMF generated in this solenoid? Okay. So same idea, right? EMF is of course flux change, the rate of changes of magnetic flux linkage. So NBA cost 30, right? Cost 30. Okay, keep on moving. So over the time. But here the problem is the B over T, P changing, B over T is actually 0.4. Okay. Magnetic field over the time is 0.4. Okay. So N is 600 turns. A is the pi r squared to be used because circular pi r squared. So we get 1.63 volt should be generated. Okay. So this question is slightly different because the B over T packed together to give you the magnetic field strength, rate of change of magnetic field strength. Okay. Okay, so EMF can be generated either you turn the coil or change the strength of the magnetic. Okay. Okay. So more question to strengthen the idea. Eh? Any part you don't understand here? Okay. Here we go. More questions. Okay, so magnet is oscillating. Yeah, the magnet is oscillating, and this magnet will start to move. Why? Speed and speed, the polarity of the solenoid at A, B, C, and D, when the bar magnet P moves towards and away from A. Okay, first, when the north pole moves towards A, what type of polarity of the magnetic field? A will be north, right? Opposed to change, right? When the north pole enters into the magnetic field, the coil must oppose the change. Okay, it must create a force upwards, right? So how we can create a force upwards? By creating a north pole here. Okay, and go down, create north pole, so difficult for us to move down. It opposes the change. You don't want me to move. Okay, so go down. When you go down, up will be north pole. Okay, so try to stop you. Okay. Then, if here north pole A, B will be south pole, right? North pole, the up means down is south pole. So north pole, south pole. So north, south, then go down. What is D will be? So up, north, down, south means right hand grid rule. Current should flow this direction, right? The one indicated in the diagram. Okay. So current flow here, like this, right? Going downwards. So right hand grid rule here again. So this is your direction of the current, right? So your thumb points to the north. So D should be north, right? So A north, B south, B north, C south, and the bar magnet moving downwards. Okay. Right. So A is north. When the bar magnet moves upwards, A will be 1. And when the magnet wants to move away, flux is changing. You want to oppose the change. You want to stop the movement. So what pole you can create here to stop it from moving up? You attract, right? Pull it back. So here A is going to become south. When the magnet moves upwards, A become south. So the magnet approaching, it will repel it. Yeah? And the magnet moving away, you try to pull it back. Its mission is to stop the movement. Okay. So when move up, north pole moving away, A will be south. Okay, south. And B north, and so on. And the direction change. Okay. So here D changing north south at the same frequency of this oscillation. Let's say this oscillation is 50 Hertz. This pole at the D going to change north south at 50 Hertz. Okay, 50 times in a second. So what happens to this magnet? Here the pole is changing continuously, north south, north south. What will happen to this magnet? Magnet start to oscillate. Okay, with same frequency as this oscillation. The same frequency as this oscillation. Okay. So I told you what is the polarity of the magnet. Okay. And describe the motion of the bar magnet at Q. Yeah, Q going to oscillate as the same frequency as the oscillation of the initial magnet. Okay. So that's the idea actually. Okay. This shows just going downwards. Going downwards, north, south, north, south. Going upwards should be the other way around. However, the bar magnet will be set into horizontal oscillatory motion. Same frequency as the oscillation of the magnet. Okay. Okay, this involves Faraday's law and Lenz's law, of course. The direction of the current, you have to link the Lenz's law. Okay. 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 So the key idea will be continuing now. The EMF is rate of changes of magnetic flux linkage. Now this diagram is not a coil. It's not a coil. It's just a conductor. Conductor here. Okay. This conductor was moved to the right. Okay. Moved to the right. Just shifted to the right, cutting the magnetic field line which sected into the pitch. Okay. So let's say the conductor when moved to the right, it cuts the magnetic field line. Okay. So EMF should induce in this conductor. EMF should induce in the conductor because flux is changing. Okay. So what is flux? B dot A over the time for you to move. B, the strength of the magnetic field. But now the A, which area to be used? The area, which area? Because it's just one conductor. It's not like a coil, find the area. It's just one conductor. So which area to be used? The area is swept. Okay, which area is swept? Okay. In this case, if we move from B to from here to here, let's say, so this area is swept. Okay. So this area to be considered. Okay. So the area is actually the length of the conductor multiplied by this distance, right? Horizontal distance. But the horizontal distance, can you write in terms of speed? The horizontal distance. Speed equals to distance over time, right? So horizontal distance, what? Speed times time, right? So the area is L, vertical length. The horizontal distance is V times the time of dt. Time, you can put time into it. So the time cancels, it's BLD. Okay. So this is the EMF induced formula. This is a formula to find EMF induced in just a conductor, not a coil, just a conductor. You swipe. What is the EMF induced in that conductor? So BLD depends on the magnetic field strength, it depends on the length of the conductor, depends how fast you move the conductor, generate EMF. Okay. But this formula originated from Faraday's law. Rate of changes of magnetic flux linkage is the EMF. Okay, so remember many questions with just a conductor moving around. They ask me what is the EMF induced? BLD. Okay. You know? So that when you move here, a conductor, which direction the current induced in the conductor, which direction the current flows in the conductor. Another way of finding is Fleming right hand rule. Fleming right hand rule, you can use, don't use left, left for motor. So right hand rule for generating EMF. So when you read the question, check first, is it motor or generator? Motor means you get force. Generator means you get EMF. Okay? So this conductor is a generator. Fleming right hand rule. Okay? So I say FBI. Okay? Yeah.
So how come sometimes the EMF going negative is run?
As I said, you don't want to include negative. Okay? Cambridge, as I said, what I told you, is always changes of flux over the time. Changes of flux, we just make it as positive. Don't need to put negative. Okay?
Therefore, poses knowledge we can use positive as well.
In this topic, all are generated. You don't have to, because all are generating EMF. Okay? So straight away put flux change over the time. Flux, right? Big minus small, make it positive over the time. The answer will be positive. That's what the marks put in Cambridge. Okay, so here, because the V is to the right, so your force is to the right, the magnetic field is into the page. F, B, I, F is to the right, B is into the page, so current should be upwards. Current should be upwards in the conductor. Okay. Okay. So this is different because just a conductor, one conductor. Okay. So long essay again. I just go to the diagram and explain to you. Okay, the long essay just now talking about this movement. Okay. Okay, let's see. This is also an interesting question, talking about Lenz's law and Faradays. Okay, there is a theory There is a rectangular coil ABCD. It is moving to the right. There is a region of magnetic field. You're going to process the magnetic field. When you process the magnetic field, of course, EMF will be generated. Now, the AB is about 5 centimeters away from the magnetic field. Okay, the AB and the BC dimension is given. Go to the question. So yeah, the AB is 10 centimeter. So BC is 5 centimeter. So this is 10 centimeter. This is 10 centimeter. This is 5 centimeter. Okay, 10 centimeter, 5 centimeter. Okay, now I do the summary for you. The speed of the trolley is 100 centimeter per second. Trolley moves forward with 100 centimeter per second. Okay. Okay, good. So that's all we need. Okay, part A. Still to explain whether there is induced EMF in the rectangular loop when the leading edge BC is traveling 0 to 5. Is there any EMF induced when the leading edge BC travels 0 to 5? No EMF, right? Why? Answer? No changes in magnetic flux linkage, so no EMF induced. And we explain, try to include this term, magnetic flux linkage, what happens. Okay. So 0 to 5, no EMF because no change in magnetic flux linkage for the coil, so no EMF induced. Okay, 0 to 5, no EMF, right? Okay, never even enter into the magnetic field. Okay, next, 5 to 10. 5 to 10. Okay, and the coil BC move 5 to 10. EMF will be induced, right? When the BC move from 5 to 10, okay, which direction the current will induce in this coil? Clockwise or anti-clockwise? This Lenz's law. 1 minute for you. The coil move from 5, the BC move from 5 to 10. Okay, halfway inside the magnetic field. What direction the current will induce in this coil? Clockwise, anti-clockwise? Lenz's law. Lenz's law state what? The current always opposes the change. What change happens here? Flux rising or flux decreasing? When move from 5 to 10. Flux rising or decreasing? Flux is rising, right? Flux is rising. More area going to overlap with the B. So flux is rising. So current must do what? Decrease the flux or rise the flux? Decrease the flux. How you can decrease the flux? How we can decrease the flux? Create a magnetic field, same direction as the original magnetic field, oppose the original magnetic field. You want to decrease the flux, so oppose the original magnetic field. Yeah, magnetic field which direction? Into the page. So the current must produce magnetic field which direction? Out of the page. Because we want to decrease the flux. Why the current want to decrease the flux? Because flux is rising. Okay? We oppose the change which produces.
Can use flux and flux linkage like interchangeably.
Yeah.
Can use flux and flux linkage interchangeably.
Safest way you say flux linkage. Okay? Because flux linkage and VA and one also flux linkage. Yeah? Better use flux linkage. So BC goes from 5 to 10. So current is clockwise and anti-clockwise. This oppose this magnetic field. So magnetic field should be into the plane. So current should flow clockwise direction. Okay? And those got clockwise good. Okay? So B to C, EMF is induced because flux is changing. Okay? Current flows clockwise direction because according to Lenz's law, the induced direction, induced current is such as to oppose the change. Okay? Therefore, should be clockwise direction. Okay? Okay then. So the current flow clockwise from 5 to 10. Okay? Then 15 to 20. Is there any EMF change? 15 to 20. 15 to 20. Is there will be any current? Is there will be any EMF induced in the coil? 15 to 20. 10 centimeter. When the BC is at 15, the entire loop already inside the magnetic, right? Then 50 to 20, the entire loop still inside the magnetic field traveling, right? So is there any EMF induced 15 to 20? No. Yes or no? What is EMF? EMF is rate of changes of magnetic flux linkage. Is there any flux linkage? Any changes in the magnetic flux linkage? No, no change. Same N, same B, same area overlapping, right? So no change in magnetic flux linkage. So 15 to 20, no EMF will be induced. It's completely inside the magnetic field. It's completely traveling in the magnetic field, but the NBA no change. Okay? No changes in magnetic flux linkage. So 15 to 20, no EMF induced. Okay? In exam ask, 15 to 20, no EMF induced. How do you answer? Because Faraday's law state that EMF only induced if there is a change in magnetic flux linkage. There is no change in magnetic flux linkage. Okay, so important is the 15 to 20. So 15, the entire thing is here. Okay, 15. So it shift to this region. Okay, so the area overlapping still the same. Okay. So if I go to the answer, BC is between 15 to 20. Mark both BC and AD are in the magnetic field. As the EMF induced both sides, this is another way, each other, then there is no induced current in the rectangular loop. It just says no changes in the magnetic flux linkage. Okay, now last one, 20 to 25. Is there any EMF induced? 20 to 25. So the BC from 20 go to 25. Halfway leaving the magnetic field. So flux is changing or flux is changing. So current flow now in which direction? Clockwise and anti-clockwise. When move from 20 to 25, flux dropping or rising for the current? Flux is decreasing. So current should rise the flux. So how we can rise the flux? Create a magnetic field, same direction as the original magnetic field, right? Original magnetic field is into the page. They must create flux is dropping. I need to rise the flux. So same direction should be clockwise. Okay, yeah, so that's the question A. Okay, now B. Calculate the EMF induced in the rectangle loop when move from 5 to 15. Go back 5 to 15. 5 to 15, okay. From 5 we move to 15. What is the EMF induced? When you get 5, flux is how much? And the BC is at 5, flux is how much? Magnetic flux linkage, 0, right? When we go to 15, the flux is the maximum, right? The NBA. So yeah, so final flux minus initial flux, or changes in flux, big minus small. Okay. Over the time, what is the time? How do you get the time? The speed is 100 centimeter per second, right? So from the speed you can find the time. Speed, if you travel 100 cm in a second, here travel only 10 cm. So 10 cm, what is the time taken? 100 cm 1 second, 10 cm is 0.1. 0.1 second. Time is 0.1. You get it from the speed, right? So you can find the EMF. Rate of changes of magnetic flux linkage is your EMF. Okay, so that's the working here. We've done this many times. Okay, I hope you got the idea. Okay, class. So the next lesson we go about the graph. We're almost done. Another one lesson, then we will stop. Okay, let's stop it. Okay.